Hello, everyone. Welcome to the Carnegie Mellon Graphics Colloquium. We invite world-renowned researchers each semester to give a general CS audience talk on the past, present, and future of computer graphics. And today, we're honored to invite Professor Karen Liu from Stanford University. Karen has made significant contributions in developing computational methods for simulating realistic and natural human motions. Her work extends to formulating complex control policies for humanoids and assistive robotics, as well as enhancing core algorithms in numerical simulation and optimal control. She is recognized as one of the young innovators under 35 by Technology Review and a distinguished member of the ACM SIGGRAPH Academy. Please join me in warmly welcoming Karen.
Thanks for the nice introduction. Yeah, and also it's really great to come back to CMU. I was here 2018 giving the RI seminar talk, but Brian just reminded me it was 2017, November. Yeah, but it was great to come back. And today I'm going to talk about building large models for predicting human motion. This topic touches almost everything we care in our lab, the movement lab, which I direct at Stanford. So we're very interested in motion intelligence by creating coordinated, functional, and natural movements for digital humans in simulation and also for physical robots in the real world. Our research touches many different disciplines, and the application domain is also really broad. So if we are able to predict human movements, we open up a lot of potential applications, healthcare applications, from sport medicines to exoskeleton design. And being able to synthesize realistic human movements can directly improve fidelity of a lot of digital human applications using VR, AR, or video games or films. And studying human motion also has significant impact in robotics because now we can teach robot how to interact with humans or teach robot how to move like humans. So currently there are 4 research directions that we are interested in the lab. As you can see, the common theme here is the word human, right? Improving the life of a human life quality is the core driver of our research, and that's why we focus on the physical, how human exists in the physical world, not the online world. And we are interested in the interaction, the physical interaction between the environment and the humans, and the physics that drives the interaction. All right, so I'm going to first focus on the digital human part of my work, and toward the end, if I have time, and I will talk about the human dexterity. So in the past, we have been building a lot of physics-based models to simulate motion. We usually would design a control policy which determines the muscle activation or joint torques that will be applied to the physics simulator, which will generate motion at the end. And this control policy is where I envision that the motion intelligence is encapsulated. And this kind of model gives us a lot of interesting applications, right? We can, teach our agent to perform very complex tasks that looks very compelling. However, when it comes to predict the movement of a particular person interacting in the real world, we really don't have any clue whether our simulation models or physics engines is in any way reflecting reality. But one thing we do know is that if we don't consider real-world human data, any of our physics model that we created will be useless to anyone, pretty much. So building this data-driven models of human motion, the model for human motion has indeed become the mainstream techniques that drastically changed the field of computer animation and robotics in the last I would say almost 2 decades. And specifically in my lab, in the last 2 years, we've been playing with this generative model that's trained on large-scale human motion data to predict human motion without physics, underlying physics model. So here is one example. We published this work at CBPR last year. Our goal is to train a generative model to imitate human ability to dance to music. if we view generating human motion as a similar process of generating language, then we can use a lot of similar machine learning tools like transformer-based diffusion model here to synthesize a time series of poses. And for this project, we also want this diffusion model to be conditioned on music. So to train this diffusion model, we need to have a paired data that has a correspondence between the music and 3D poses. And with that, we're able to generate some interesting results. All right. So here you can see that if we play a different music, like a music that the agent never heard before during training, the motion will be quite different. But you can see that the agent was able to pick up the rhythm and the beats and the style of the music pretty well. And really interesting thing is there's no physics behind any of this. And we can play very different genre of music. My students thought I grew up in this genre. I don't know how old they think I am. And one really interesting about diffusion model is that it gives you this online editing capability during inference time. I will talk a little bit more on that, but for this particular example, here we ask, after we train the model, we ask the user to provide the lower body motion and ask diffusion model to fill up the rest of the motion, condition on music. All right. So it works very well for this project, but as I mentioned earlier, paired motion data set doesn't always exist for the model you want to train. So for example, in this project, we want to know if we can estimate the full body human motion from a single egocentric head-mounted cameras. So the input will be the videos that camera that you wear sees, and the output will be your full model. So basically from what you see, we wanted to guess what you're doing. And then we train a diffusion model for that, which is, we have a small set of paired data from video to 3D motion, but it failed almost immediately because the data set is just not big enough. So we decided to turn this into a two-stage process. For the first stage, we will train a model from video that transform video to the head pose trajectory. So translation and orientation of the head. And that's pretty much a SLAM problem, right? Which is great because now we can, lean on a lot of existing techniques. And the second stage now goes from the head trajectory to the full body motion. And now because we're, both input and output are in the 3D world, right? So we have a lot of data. We can bypass this correspondence between video and 3D data. And now we have a lot of data. We could train the diffusion model just fine. So here is some input, some results. This is what the character is seeing, and we want to guess what the person is doing. And our result is shown in this the blue character comparing to the green ground truth. And then you might be thinking that, well, this is a really underdetermined problem, right? Because if you give me input like that, I can do there are infinite solutions, infinite possible motions that match that input. And you're definitely right. And that's why the generative model is a really good choice, because generative model doesn't force us to map an input to a specific output. Rather, we can map the input to a distribution of output. So all these data, all these motions are plausible according to our generative model. All right, so after investigating these generative models for human motion in the past 2 years, we're quite convinced that human motion, just like videos or text, has this spatial and temporal structure that could be easily exploited by the generative model. So the natural next question would be, if we have a significantly amount of more data, human data, can we learn a large model for human motion analogous to ChatGPT for natural language? So in my view, in my vision, I see this large motion model as the foundation model for all applications that involve human motion prediction. Just like a large language model, when feeding a random seed, this large motion model will generate infinitely long motion sequences that are random, but they are similar to the training real world data. And we can ask this large motion model to predict kinematic information like poses and joint angles. which is great, but we can also ask them to predict dynamic information like contact forces, joint torques, or muscle activation, basically the physics behind the kinematic information. And this large motion model can be conditioned on practically anything, right? We have seen that it's conditioned on audio, on video. We can also make a condition on text. And if you have a labeled medical data, you can make a condition on biomarkers, and then you can predict the impairments in the human motion, human movements. And of course, none of this will be feasible if we don't have data. And we need to have a very large-scale, diverse data set. When it comes to, think about internet scale training data for ChatGPT. So what does that mean for human motion, like internet scale human motion data set? Well, definitely it has to be large scales, hundreds of hours of human motion, that's for sure. But we also need the data to be very diverse. It has to cover a wide variety of human activities performed in a diverse environments, like cleaning my apartment, setting up the dining table, or trying to get into the car while holding a coffee cup. So all kind of emotion in context with the environment is needed. Unfortunately, the current motion capture pipeline is designed like mocap system that I know CMU has a few of those. They're designed for capture small scale human data with only one person, one subject in the scene and without the environment context. So using this current motion capture pipeline technique, computer graphics and computer vision communities have already, collect a decent amount of the data shared with the public. The problem of their data is that it only contains kinematic data, kinematic information. There's no dynamics behind it. So what is the dynamic information? I kind of talked a little bit already earlier. Start off on contact force, ground reaction forces. In this case, we could extract the joint torques and then do inverse dynamics to get muscle activation. So that's kind of dynamic information we want. But you won't get that from a lot of like a CMU motion capture data set does not have that. Biomechanics labs are usually equipped to capture dynamics information. But if you look at the the data set from biomechanics community, they have tons of problems. The first problem is their data sets are usually very small in size, and that's usually because to process dynamic information is very labor intensive. And they're also very heterogeneous, right? Like they usually design their data set specifically for that experiment they care about. And maybe that's why data sharing is never a practical, it's not a popular practice in biomechanics, because they never thought that anyone else would want their data. But we do. So we propose a solution called AbBiomechanics, which is a web-based tool that can automatically process the raw motion capture data to generate accurate, scaled and fitted digital twin of the subject and matched kinematics and dynamics motion. So this is a landscape of human motion we have today. We have some shared data sets shown in green, but a lot more unshared data collected by individual labs or studios shown in gray. And because AbBiomechanics is fully automated, it can expedite the data collection cycles from days to minutes. And that gives researchers chance to capture more data more easily and quickly. And because AbBiomechanics handle this entire data processing pipeline, the data the output data is by default harmonized and compatible with machine learning tool chains. And to promote data sharing, we let people use AbBiomechanics free of charge in exchange for their consent to donate their data to the public. So we really believe that with AbBiomechanics, we can harness and aggregate this data collection efforts from different labs and different studios and create this unprecedentedly large and machine learning ready human motion data set to do interesting research. So what is this unique feature of AbBiomechanics that make people want to use it for their data processing? I mean, don't we already have a lot of commercially available data processing tools? Well, this is actually a misconception, I would say. First, the existing data processing pipeline is not really automatic. If you say it's automatic, because you've never really done that. If you really try to work with it, there's just so many steps that require human intervention. And second, the current data processing pipeline is incomplete. It stops kinematic motion. A complete data processing should go all the way to joint torques, to the muscle activations. And so how do we make the pipeline more complete? If we follow the conventional approach, we will, process the data stage by stage, sequentially. And the problem with this approach is that there will be error, created. Could be, error due to the model, due to the data. But every time you create a data, you create an error that would propagate it to the next stage and eventually accumulate it at the end. It becomes very difficult to fix it at that point. So the right thing to do is to consider all the variables at once. We could formulate a joint optimization that simultaneously solve for the joint angles, the marker locations, the bone scaling factors, body mass, joint torque, contact force, and muscle force. And as you see that, as I go down the list, you know that this optimization is going to be super large and horribly non-convex. And it's going to be very, very sensitive to your initial guess approximation of the solution. And that's definitely true. So previous work has tried many different heuristics to approximate this initial guess. And in general, if you're solving a problem like a locomotion walking, heuristics can go a long way. But if you're doing something that's less study, right, like yoga or some kind of a exercise motion, then a lot of heuristics would not work very well. So essentially, the technical challenges boil down to finding a kinematic motion that matches this physical equation exactly. So here we write down this Newton's second law in the Lagrangian formulation. In general, we have two different types of sensors, right? We have a motion capture markers, and we also have force plate sensors. And these two sensors will give you two versions of ground truth. Let's just say we plot the center of mass trajectory over time, and this block curve here is the actual ground truth. If you believe that your motion capture system markers that you collect more, then you can, based on that, you can compute the joint angles, and plot out the center of mass trajectories. You get this green curve that's kind of close to the ground truth, but there's errors here and there. If you believe your force plate sensors, then you will get another version of ground truth, which looks smoother, but it's kind of far away from your actual ground truth. So that's why people usually start out with the motion capture solution, and then try to figure out how to fix that solution based on using the force information as a soft guidance. But if we plot the center of mass trajectory in the acceleration domain, you can see that now the purple curve is a lot closer to the ground truth. And that's because that any little error that you make in the position domain is going to generate these huge spikes in the acceleration domain. And that is actually a big problem when you want to solve the problem. You try to solve an optimization based on the motion capture marker information, because the gradients that you're going to compute is going to be very unstable. So since Newton's second law is described in the second order differential equations, we found it much easier to start out with the purple curve, which agrees with the dynamics, and then try to fit that purple curve based on the information we get from mocap. And if you work out the math, essentially we're solving a passive dynamic system expressed as a linear system instead of a quadratic program which has this really unstable gradients. So with that little twist that we did to have a better initial guess for our non-convex optimization, we can get a very accurate kinematic and dynamic information. And AbBiomechanics is also very robust across different types of motion. So now we have a fairly large data set, 70 hours of human motion. That's not just kinematics, but also a matched dynamics with the matched skeletons in there. So here's more visualization of a motion reconstruction. This time we actually also solve inverse dynamics to get muscle activation. And quantitatively, AbBiomechanics can indeed save a lot of human labor to the post-processing. It also generates very accurate results. AbBiomechanics has been released to public for a little bit more than a year, and we have seen a rapid growth in the user base, as well as the data being processed and shared to the public. So if you are researchers interested in human motion, please give it a try. This is really that simple. You just go to the website. It's a web tool. You don't even need to install anything on your computer. You just drop your raw motion capture data. You come back, after a few minutes, you will get your fitted digital twins along with the kinematic and dynamic motion data. All right, so AbBiomechanics gives high quality motion data, but we don't want the data collection effort to be constrained in the lab. And to scale up, we must be able to collect high quality data in the wild where people wear portable sensors everywhere they go, whole day long. All right, so that's why we're trying to build a portable motion capture systems based on 6 IMUs. So the idea is that we don't want the motion capture system to be invasive to people's regular activities or have a third-person view camera following you around. And this IMU-based motion capture system can generate full body motion in real time from 6 IMU sensors. And of course, 6 IMU sensor is not enough of information, not to mention that IMUs could be very noisy and drifting over time. So that means we need to use a machine learning-based model to reconstruct the data. And thanks to AbBiomechanics, now we can build those machine learning models using really high quality human motion data. So here's my students stress testing the 6 IMU system. The motion reconstruction is pretty accurate. You can see that it's real time. And even when he's trying to do something out of distribution, because underlying this is still a machine learning base. So there is a distribution that we use for training. Now, this year, we take our IMU motion reconstruction to the next level. We want to be able to have a single motion reconstruction model, agnostic to where you put IMU sensors and how many IMU sensors you use. Basically, we want to have the flexibility that allows us to determine where to put IMUs and how many IMU you use on the fly based on the motion of interest without the need to retrain the model. So we use a diffusion model to give us this capability, the flexibility I was mentioning. Recently, we have seen a lot of diffusion model in the image domain, right? Like DALL-E, Midjourney, they train diffusion model to synthesize images from just noise. And one powerful feature of a diffusion model, you probably all know this already, is this ability to partially edit the image during the inference time. So here you can mask part of this image, and then you ask diffusion model to come up with what's being masked, and that's harmonized with the rest of the image that you provided. And because this diffusion model is a generative model, if you give it a random seed, different random seed will result in very different output images. Okay, so how does that relate to human motion? If you imagine human motion is an image, every single column of that image is a particular pose. Then we can just directly use the diffusion model framework to generate human motion from random noise, which is basically just gibberish, random poses. Okay, we can also use in painting here. So for example, if I provide the upper body motion, so the upper body motion looks more reasonable at the beginning, and lower body motion is just random noise, I can ask the diffusion model to fill in the lower body motion. That's what we did for that dancing motion I showed earlier. For this IMU project, though, we want to do something different. So during training, we're going to train a diffusion model that can denoise the entire set of IMUs, which has 16 of them. Okay, 16 IMUs usually allow you to reconstruct pretty well. So during training, we wanted the denoiser to learn all the how to denoise all the IMUs. Each of the IMU here trajectory is one row here. But during inference time, It depends on how many IMUs you might have. Like in this particular case, I only have 3 IMUs, and I put in, you can determine where you want to put it. I put it on the left side, right knee, and right, or the other way around, left elbow. And then I can just ask the diffusion model to fill in the rest, and I get a full motion. But we want to do a little bit more than that because we want to have a real-time reconstruction. So essentially, we want to build an auto-regressive model. We only predict the next frame, and then from based on the history of the motion that was also predicted previously, and that's what we end up doing. Okay, so here we're showing that my students able to just test this real-time motion generation. He started out with 6 IMUs, then he removed 2 IMUs and do the same thing again without retraining the model. It's the same diffusion model that allows us to have this kind of flexibility. So people can decide how many IMUs they want to use based on the motion they try to capture. Okay, with cheap sensors like IMUs and machine learning-based reconstruction technique, we can now collect the data from anyone, anywhere, anytime. But we're still interested in collecting data in a very rich contextual environment. So for example, can I capture someone's motion, someone putting the luggage into the overhead bins on an airplanes, or cleaning the apartment building? So the key challenge here is to simultaneously capture the human movement together in the context of the environment. And that's what we did in this project. We invent a new data acquisition motion capture system. We want to be able to capture someone in a very clutter environment. Like in this case, the person is trying to pick up something behind the toilet in the bathroom. And not only that, we want to be able to capture the egocentric view, what the person is seeing while he's doing that. So this will give us a chance to answer not only the question of how people move, but also why people move in such a way. So how do we do that? Well, we can go to the motion capture lab, build a bathroom set scene in there, and then capture the motion. But quickly we realized that the occlusion caused by that, the physical scene you build, is going to make the data acquisition impossible. So our idea is to combine VR headset with the mocap system. The subject will wear the VR headset while being motion captured. A contextual virtual world is streaming to the subject's VR headset to create this illusion of being in this cluttered indoor environment. We then ask the subject to do things that engage the environment, like look for that red toy truck in the closet, or pick up that pencil that roll underneath the table, right? Something that really show off the engagement with the environment. And so here is the video of one of our data collection session. As you can see, the immersive virtual perception can induce very realistic behavior. The person is trying to get to the, behind the, I don't know what, I think I asked the person to unplug something there. And this is what actually happened in the real world. And another really nice advantage of this method is that we can construct a very variety of different scenes very quickly and very cheaply, comparing to building this movie set in my mocap lab. So we collect more than 10 hours of navigation and reaching motion in 9 different scenes, and we call this data set Circle, and released to the public early last year. This is also a CVPR. So having a data set like this allows researchers to train virtual humans who can maneuver their body in a very non-trivial way based on the egocentric observation of the real world. And that kind of opened up a different kind of research people could do. So while Circle continue to expand, there is another dimension I have not talked about. For some applications in biomechanics and computer vision, we need a more detailed human models. Beyond just the bare minimum skeletons that we usually use. And human spines and shoulder complex are one of the most complicated anatomy in human body. But unfortunately, this is also the part of a human body that's being overlooked all the time. So when I say torso, I mean both the spine and also the shoulder complex. In biomechanics, detailed modeling for parts of the torso exists, but when you want to have a whole upper body model, people usually treat it as one rigid piece. In computer graphics and computer vision, we have the opposite problem because every single joint we use is as ball and socket joint. It's a 3-DoF degree of freedom. So we have this unrealistically flexible torso. So really, today, we don't have a good torso model we can trust. And this is unfortunate because when you look beyond locomotion, there are a lot of human activities that require complex spine and shoulder movements. So in this project, we want to model all of these. We want to model the vertebrae, the disc between vertebrae bones, and the facet joints and ligament joints. And also, for the shoulder complex, we will model the clavicles, the speculus and bones, and also the rib cage. To be able to simulate all these new elements in the human body, we need to expand the current physics engine with a new functionality. So first, we need to be able to simulate new type of constraints so that we can model this facet joints correctly. We also need to incorporate finite elements methods to simulate this deformable discs. But when you put the bones, the vertebrae, which is a rigid body, and those finite elements disc together, you stack them into a long chain. Min Chen will tell you that this is not a very good idea because the simulation will become very unstable and also very slow for kind of a complex control problem we want to solve. So we have to deal with that, we would basically implement the variation, projected dynamics and impulse-based dynamics to solve those problems. But let's just talk about application here. So once we have this new spine model and new physics engine for the spine model, what can we do with it? So one thing we can do is we can take an existing motion capture sequence, which doesn't have any complex movement in the torso area, and then we can retrofit that existing motion capture sequence with complex and detailed and physically correct torso movements. And basically, we're solving an optimal control problem in this torso area with the boundary conditions that was given by the existing motion capture sequence. So with that, we retrofit 1,300 motion clips from public mocap data set. So now we have a new motion capture data set that has the really rich torso upper body movements. So we call this detailed human skeleton simulator spine, and this is built on existing physics engine, also created in my lab. DART is a generic articular rigid body simulator, and Nimble Physics is a differentiable version of DART. Now, detailed skeleton is crucial, is critical for healthcare application, but in computer vision and computer graphics, people arguably care more about the outside, right, the shape of the body rather than the interior skeleton. And that's why we have a model like SMPL. I'm sure a lot of people here know SMPL and also use SMPL. It's a really nice parametric body shape model created at MPI by Michael Block's group. But the skeleton used by SMPL, I don't know, have you ever looked into the skeleton of SMPL? It's very unrealistic. Just like I said earlier, everything is ball joints. This thing is, unrealistically flexible. So what we want to do in this project is to take SMPL, but swap the skeleton to a biomechanically correct skeleton. And this is a collaboration with Michael and his student. So basically, we look at amass data set, which is one of the largest motion capture data set, and we refit SMPL with a better, more biomechanically correct skeleton, and then recreate this data set. We call it bio-amass. From outside, you probably don't see any difference. It's SMPL, but all the skeletal motion inside is correct now. Okay, so with a large, diverse, and high-quality human motion data set, is this enough for us to, create a ChatGPT for human motion? I I wish this is true, but it is not. So let me explain why this is not the case. I mean, the last couple years, or maybe even more than that, we have seen a lot of attempts to create this large emotion model. Maybe it's not as large as I hope, but it's it's pretty sizable. It's a generative model. It's also the people call it motion prior. Here's one example. This is built by Stanford by Leo Guibas's group. It's called Humor. And you can see that this is a generative model. Even it's not when it's not conditioned on anything, it's just gonna just randomly walk around. And it's just gonna do that forever. But the biggest problem, the problem I have with this kind of model is it doesn't respond to physical events. Like when I'm throwing the balls on the character, there's no any of the physical response to that. And of course, there's no physics. There's no notion of physics behind it, right? So how can we expect that respond physically? So maybe we dump our physics model too quickly. It would be really great if we can motion models with a physics simulation or physics model. This way, our agent can make good decisions based on a large motion model, but at the same time, it can respond to physical events because it's physically simulated. But putting these two things together is not as easy as you think, because essentially they are doing the same thing. These two models are both predicting the next frame, the next pose. So one way we could do it is to just treat this large motion model as a high-level policy, which will output as suggested the pose for the next frame, and then train a low-level, maybe RL, reinforcement learning control policy to track that pose. And then, because RL can control physics simulator, when there is a perturbation or physical events, the character, the agent, will respond to the physical events. So we did exactly that in this project. We use a high-level policy is a diffusion model in which we generate those poses, and then we train RL policy to track those poses. And now this way we have a physics-based character, which is nice. And then when you're throwing things around, you get a little bit of head bobbing, and then there's some response to that. I would say this is way too stiff, but still, it's response. Okay, so this is fine, but I always feel like using RL to do just tracking is an overly heavy-handed approach. I don't know what other words I can use to describe that, because if you think about that, the RL this low-level control policy doesn't have any intelligence. Right? All it does is just to track a pose, and in a way, to track a pose that physics engine can simulate. And we know physics engine is flawed, right? There's some good stuff in the physics engine. It follows F equals ma. That's good. But there's also a lot of bad stuff in there, right? Like all the contacts, a lot of things is approximated or even incorrect. So training RL, it's not easy. I know some people here can train RL better than others, but it's in general not easy. And then you just train that to handle this physics engine, which we know is probably not correct. It seems wasteful. And the hypothesis here is that we think that most of the intelligence is encapsulated in this large motion model, including those decisions to recover from perturbation. It's just we don't know how to bring it out. All right, so maybe we can just bypass this low-level RL policy altogether and invent a new physics engine that can directly interface with a large motion model. And that's what we did in this project. So we call a drop, or I call it simple physics. So basically, if you can see that now, if we directly interface with large motion model, we are handling the input to the physics is a state rather than a control or action. This means that we could just treat the large motion model as an energy field and then reformulate this problem similar to what I mentioned that we do a lot with a variational integrator, so we can directly solve for the next pose instead of using the conventional for integration to get the next pose. All right, let me just show you the results. So now we still use the same motion prior, Humor. It was trained by someone else, but we just add a little bit of physics to it. And now you can see that the person start to interact. And note that all those active control decisions are still made by the large motion model, which decides how the agent respond to the predation and how it returns to the data distribution. So where the physics doesn't make any decision, there's no intelligence in there, but all this the motion prior that was trained by someone else has that. So now, in this example, we add a spring force between the red ball and the character's hand, and we start dragging this red ball faster and faster. And now you can see that basically this large motion model being prompted to generate interesting output than just random aimless walk. And here another example is to tilt the direction of gravity. And when we did that, the large motion model reacts by making the agent crouch down and stick arms out as if it is trying to regain balance. And that's a surprise to us, right? Again, there's no auto control here, no auto controller making decision. It's all coming from the large motion model. And here we add obstacles on the floor, and you can see the response to that. And what if you put the two agents together with both of them controlled by large motion models? You can see that there is some response to that. But remember, these are generative models. So if we use a different random seed, the same scenario can cause very different results. Yeah. Okay, so I hope you are intrigued by these generative models as I am. You might think that these models are never good enough for generating physically correct motion. But this is true, and I agree with that. But the important thing to note is that right now we are only feeding those large motion models with kinematic information. Imagine with AbBiomechanics, we can have a paired kinematics and dynamic information. If we start training large motion model with that kind of data, with the dynamic information, maybe one day we can truly dump our physics model and then use just a data-driven model because it learns what physics looks like. Okay, that's what I want to talk about today related to human motion. In the remaining of the talk, I want to quickly talk about what we did to create human-level dexterity for robots. So recently, we have seen increasingly more capable dexterous robot hands thanks to advances in hardware and both in algorithms. So having an opposable thumbs, multiple fingers, and the palm can really have a lot of advantages, right, over those grippers or simplified robot hands. But these advantages also come with unique challenges. So the first challenge of dexterous hand is that they are, sorry, did I say challenge? I mean advantage. The first advantage of a dexterous hand is that they are flexible, right? You can assume different configurations that perfectly conform to the shape of objects you want to manipulate. But this advantage comes with a price. The first thing is that the kinematics becomes very complex due to the high degrees of freedom. And the dynamics also becomes very complex because now when you talk about grasping, you have to talk about force closure, you have to talk about the friction cone constraints. And lastly, the solution space of valid contacts between the hands and the objects are also very complicated. It's multimodal, and it's combinatorial. So if you want to solve a problem in optimization with the contact modes, it's just hard. So my student Albert proposed a method that synthesizes robust and diverse dexterous grasp by learning a generative model combined with a bi-level optimization. So this hybrid method utilizes CVAE, conditional variational autoencoder, and a bi-level optimization to solve those dexterous poses exactly. And we can also pick up objects that are adversarial. Why is adversarial? Well, the spike ball is very bad for suction cup. And the sandwich box is really bad for parallel jaw gripper. So we deliberately picked those to demonstrate that you do need the hands like a human. All right, so that's the first advantage and the first challenge. The second advantage of a dexterous hand is that they are very versatile. They can dig, shove, pick things, do insertion or reorient. And the same hand can perform all these highly different tasks in one sitting without the need to regrasp or use external tools. But to truly enable the versatility of dexterous hand, a couple of unique challenges need to be overcome. So first, versatile dexterous hand manipulation require drastically different subtasks. We have to learn all that. And furthermore, it requires a long horizon planning that needs to consider the context, the temporal context of all those subtasks, as well as the functionality relationship. So my student Renpei and Chen came up with a solution to that. So let's just imagine this is a problem you are tasked to solve. Given a box of Lego, your job is to find this piece, 1x2 yellow piece, and then put that yellow piece to the baseboard at the location 0, -1, 0. Okay, so if you think a little bit closer, this requires the robot to know a number of different subtasks. You need to be able to search, you need to be able to orient, and then so that you can dig it out, you can easily grasp, and then finally you need to put it, you need to do the insertion. So naive solution to that is you just train our RL policy for each of these subtasks, right? And then when you're done training, you just execute those 4 policies one by one. And of course, anyone deal with RL would know that RL usually will fail or not become suboptimal at some stage, and then the later stages, the later policy will have a hard time to recover from that. So my students came up with, I'm just gonna kind of skip this part, but all right, I skip it a little bit more, but let's just say that during training, you need to figure out a bidirectional communication channel so those policies can talk to each other back and forth. But let me just show the results here. So now the robot is tasked to build a pyramid, a really simplistic pyramid. So first to pick up 2 red blocks in the box, and then on top of that you put a yellow piece on. And here you can see that this is the sensors of the robot. So robot has a wrist-mounted cameras, and which only gives you RGB. Yes, RGB. And then from there you need to kind of do some post estimation of those objects in a very occluded environment. Yes. All right, done. Okay, so the last challenge I want to talk about in terms of a dexterous hand is or advantage first. Advantages is anthropomorphic, which means that we have the chance to teach robot task directly from the human demonstration, right? But there is a number of unanswered questions as well. So for example, how do we scale up demonstration collection from humans? And also, how do we actually retarget the human demonstration to robot to overcome this, what people usually call embodiment gap? So in this project, my student Chan again built a portable system to capture the human demonstration in the wild. And we call this system DexCap as opposed to mocap. So here you can see that we can capture both the human motion, finger motion, wrist position. And what we're showing here is this whole process, including the calibration. So you know that you don't need to spend an hour calibrate this thing. You just go there and then move around a little bit to calibrate the cameras. And once all the cameras are calibrated, you put 2 cameras on the wrist and then start manipulating. And this way, we can collect a lot of the data fairly easily in the wild. And then we retarget the demonstration to fit the robot's kinematics to the human data, and we retarget both the actions and observations, and then train a diffusion policy. And we can now deploy this policy on the real robot like that. And the robot can now perform task of picking up the tennis ball. And you can also see that there is some generalization happening because we can, put the tennis ball in a random initial location and the basket in a different location as well. Let's look at another example. Here, the humans tries to demonstrate how to pack an object into a box using both hands. So this is a manual setting. And we demonstrate doing this using 6 different objects. And here we show that the robot can generalize the packing skills to new and unseen objects. None of these are any one of those 6 objects we used to train. Because it's packing, we need to close that. Otherwise, it's incomplete. Okay. Or what could possibly go wrong if you give a robot a pair of scissors? Well, it's hard. The robot try very hard. And when you try this for a long time, eventually something will break. So just give it a chance. Okay. All right, we need a sharper pairs of scissors. Okay, what else can we capture with this DexCap system? Well, since last fall, we started collaborating with Stanford Music Department to collect elite pianist performance. So these are people that are at the international competition level. Our goal is to collect human peak dexterity performance and study the biomechanics behind it. So we will collect more than 10 hours of elite pianist performance, and hopefully this data set will be interesting to a lot of people when we release in March. All right. With that, I would like to thank my collaborators, my students, my funding agency, and thank you for listening.
We have time for a few questions.
Thanks for the great talk. Just trying to do a back-of-the-envelope calculation that just said, I think ChatGPT took the entire human DNA, decades to generate somewhat reasonable value. For the motion model that you are going for, have you given a thought, like, does it even conform with this strategy, or some radical changes is required, or like, how much data do we even need?
Yeah, it's a really good question. And the answer is I don't know how much data we need. I do know that we need to start from somewhere. And I honestly, we are even more behind than you think, because ChatGPT or images, let's just use images as an example. In order to capture images, you need to have the sensors that are like iPhones, right? Without iPhones, we will not have ImageNet. We don't have cameras for 3D human motion yet. Well, our camera is motion capture system, which is, you can say, kind of like a camera technology in the 60s, right? You have something that's kind of working, but collecting data is painful. Developing data takes days. We're kind of like that. So that's why when we're doing this, we're not just looking at collecting data, the effort of that, but also the innovative way of collecting it, including inventing new sensors and also outsourcing, right? Farmed biomechanics researchers to collect data for us. So yeah, there are a lot of additional things that need to happen. But I think we need to start somewhere, and that's the starting point I can see right now.
My question is, why do you think we have to use mocap system to
Are you computer vision?
Because for us humans, I can see your motions from my raw eyes. That's it. I don't need any mocap system to help me to understand another person's motions.
Yeah, so I think there are two different things, right? So if it's just for understanding, right, like motion, like action recognition or anything. So yes, I agree. A lot of a different modality, cameras, for example, is great. But if you want to do something beyond that, like synthesize motion, right? Not just for analysis, like synthesize new motion, and especially learning the relation between physics and the kinematic motion. I want the data to have somewhat high quality. And vision can probably get us there. I think that's definitely, we're actually working on that as well from cameras. Can we collect high quality data? But I think right now, the key for me is that I want this model to not just memorizing the joint poses, but really understand physics, like human physics, biomechanics.
Thank you.
Hi, Professor. I had a question about new video generation models that are coming up. So they predict human motion from just video data, but there's not much evaluation done on that side. What do you think about their performances as compared to actually being 3D aware of the motion?
Are you talking about the one that was released today? Like a few hours ago?
Also previous one, yeah.
Yeah, so basically just use video so I think it's in a way a little bit similar to the previous questions. Can we bypass 3D, right? My answer to that is that, based on your applications, right? Like if I just want to have some kind of, what do they call it? Like intuitive physics or whatever, like just trying to understand, what the person's intention is, maybe we don't need to build a 3D model for that. But for my case, it's always, I want to build exoskeleton, right? I want to build something that, like a devices that people wear, and I don't know how to do that without understanding 3D and physics.
Great talk, and I think it's wonderful to not only deal with kinematics but also dynamics. My question is, when you generate those additional dynamics, how do we know they are accurate?
Yeah. Well, the short answer to that is I believe F equals ma. And if you believe in that, I can show you that we can satisfy that to, satisfy that equation to the whatever percentage I give you. It's very accurate in that sense. But of course, you can argue that maybe your joint angle is incorrect and your force sensor is also incorrect, and the incorrect becomes correct. That makes it make the equation balance. That's possible. But I think at the end of the day, what I can say is we're dealing with this disagreement between the models and data, and we do our best based on all the non-convexity hurdles that we had to fight, we had to overcome, and that's what we have. And that's one answer. That's probably the closest you can get. That's the negotiation between the model, the physics model, and the two sources of the data sensors. They might be all wrong, but that's the best we could do.
We can take one last question.
Thanks, Karen, for the great talk. About the scene in the circle data set, for example, humans interacting with scenes. For the biomechanics data set, it appears everything mostly is a single human for example, on a force plate. How would you think, if we add interaction with the scene, how would you solve, for example, the reaction force from a sofa would be?
Yeah, so I like silo all these parts right now, right? Like AbBiomechanics try to get that dynamics out of it, but Circle is not doing that, right? It's just kinematics. So my plan is that when we have enough AbBiomechanics data, we can actually train a model that predict dynamics from kinematics, and then I can use just bootstrap on that to get dynamics information for Circle as well. I don't know if it will work, but when we collect enough data, something's gonna work, right?
Yeah. Okay, so let's thank Karen again.